Dr. Najimuddin Khan with us as our seminar speaker. So just a few words about Najimuddin. He did his PhD under Professor Shubhendu Rakit from IIT Indore in 2017. And his thesis title was Exploring Extensions of the Scalar Sector of the Standard Model. And after that, Najimuddin did his postdoc at several places. So I think he was first worked as a postdoc at PRL for 1 year or so. And then he moved to IIC Bangalore as an NPDF, I believe. For 2 years, he was a postdoc there. And then he moved to ISCS, Cultivation of Science in Kolkata, and there he was there also for 2 years. And now he is working at IPM Tehran, and he is collaborating with Professor Yasman Farzan over there. So Najim has worked on several issues in high energy physics. So today he is going to talk about his recent work. So Najim, now you can start.
Yeah, so basically I will talk about, thank you for giving me this chance in this interview. Okay, so basically I'll talk about dark matter, neutrino mass in the extended singlet scalar and Higgs triplet model. So this talk basically based on this paper and this paper, these two are triplet and this is singlet extension of the model. Then I will, okay, so this actually, so my topic of the talk is first I will go through the real details of the real singlet scalar model and the extension of it and what is the outcome of it. Then I will talk about the Higgs triplet model and extension of it. I will go brief on of this model. Okay, then I will talk basically what is the progress I have done in writing the globes for the neutrino physics for the neutrino experiment. Okay, that I will talk in the last. Okay, let me go to the extension of real singlet scalar. So before going to the real singlet scalar model, let me tell you what is the singlet scalar model first. Okay, and what we exactly get in our study. So if you add a singlet scalar on the just like singlet scalar on the standard model, then and also in this model we have imposed a G2 symmetry such that singlet scalar behave like a dark matter and it do not decay to any other standard model fermion. So this G2 symmetry help to get this property, means so we can get S as a dark matter candidate. So in the presence of extra scalar, we can see that this is the extra term in the scalar potential, and for this so for this term, if you calculate the mass, we can get that this is the real mass of the real singlet scalar and this is the mass of singlet scalar, and all the other standard model fermion remains same because there is no change in their masses or any expression in the coupling. Okay, so what we achieved in this model that you can get dark matter density.
You can make it full screen, yours these slides.
It is already full screen.
Oh,
I don't know how.
So okay, then you have these left panels. Okay.
Yeah.
Okay, fine.
Okay, so okay, so what we get that in the present scenario, what we have, right, you can get relic density for this model when the dark matter mass is near the Higgs resonance region and dark matter mass when it greater than 560 GeV. Okay, most of the region is ruled out from the present direct detection experiment. So for Higgs resonance region, what we have that this Higgs protal coupling is around 0.01, but for higher mass, if you satisfy this relation with Higgs protal coupling by dark matter mass, you can get relic density within 3 sigma range. And we also check that if you can consider at very high scale that a singlet scalar dark matter as a inflaton, so you have to include a non-millimeter coupling in this model so that it can also behave like it can use as an inflaton. So it can explain all the inflation parameter. And also we can see that in the presence of the dark matter that Higgs potential becomes stable along the Higgs direction. So we have done the details stability analysis in this model. So what is the stability analysis? Let me try to tell you. So let us see. So if there is no singlet scalar, and if you have that only tree level scalar potential, then you can get the potential is like this. There is only one minima along the positive scalar direction. There is no other minima for the tree level scalar potential. But if you include the RG analysis, if you include the RG equation and the loop equation, then you can see that there is a one minima at electric scale, and at a very high scale there is another minima. Okay, so depending on this new depth of this new minima, this minima can be stable, metastable, or unstable. So when it is unstable, if the transition probability from this minima to that minima is greater than 1, then it is unstable. Or if the probability lies between 0 to 1, then it is metastable. And if the probability is just less than 0, then it is stable. Or in other words, you can say that if the transition lifetime is infinity, then it is absolutely stable. If this minima is just above here, means above this side. So, or if the transition probability is greater than lifetime universe, then it is metastable. Okay, or if the if the lifetime of this minima is less than the lifetime of universe, then it is unstable. So present data suggests that for the standard model parameter, Higgs mass, top mass, and the alpha s, all the other mass, if you consider, then present data says that this electric minima is in metastable state. And we have seen that in the presence of extra singlet scalar, it get additional correction, and it goes towards the stability. So what we got exactly in this paper, we have done this detailed stability analysis on the presence of singlet scalar. So this plot and this plot basically is the only for the singlet scalar. One can see that lambda basically goes towards negative at after some high scale. Okay, it goes towards the negative. So one can say that lambda goes negative. That means that your potential become negative. So that can be disallowed, but it is not the case. So lambda doesn't mean it goes to negative. That doesn't mean that it is ruled out or something. In that case, you have to check whether it has some minima. We have to calculate whether beta, what is the status of beta lambda. So if in that case, you have to always see that whether if beta lambda goes positive to negative, then yes, it is ruled out. But if beta lambda goes from negative to positive side, then there must be some minima at this scale or at some very high scale, depending on the parameter space. Okay, and this suggests and also you have to calculate means there is a minima, that doesn't mean also it is ruled out. So we have to calculate the tunneling probability in this tunneling probability. So if you calculate the tunneling probability, then you can see it is stable or metastable or unstable. So in the standard model, you can see that the present, if you consider this Higgs mass and top mass, then you can see that metastability of the electric vacuum basically for this particular point, that electric Higgs potential is ruled out from the stability exactly at 3 sigma. Exactly at 3 sigma, it is ruled out. So it is in metastable state. So from the stability, it is ruled out. Now what happened? What happened in the presence of extra singlet scalar? It get a positive correction, and at what stability it is ruled out, that we have checked in detail. Okay, so for this particular benchmark point where we get the relic density for 620 GeV region, we choose this kappa and this lambda, so that we can get the relic density exactly. And for this particular parameters, we see that in this standard it is ruled out at 3 sigma, but in the presence of singlet scalar, you can see that it is ruled out only at 1 sigma for this particular benchmark point, for this dark matter point. So we have again plotted Higgs potential kappa versus dark matter mass. Okay, so along this line, basically you can get the relic density within 3 sigma along this line. And one can see that we have again plotted this metastable stable region. After this region, basically this electric vacuum become completely stable, means absolutely stable. There is no metastability. And we have also plotted the confidence at what confidence level it is stable or metastable. So we have plotted this confidence level. So this region basically it decreases the metastability, and this region is just increases the stability. So this whole region basically says that in the presence of this kappa and this dark matter, it goes to the Higgs potential goes towards the metastability at this kind of confidence level. So along this line, we have changed the dark matter mass in such a way that we also take the resonance correction, means the threshold correction in the analysis. So along this line, basically the relic density also, one can get the relic density within 3 sigma. Okay, and this confidence level one can understand if this, suppose this point means that this circle basically goes toward this point. I mean, you can get this circle is here. Basically, it is allowed from the stability. So this situation. So so up to that, if in the presence of singlet scalar this is happened, so it can goes towards the star. So we have done this. Now, why we extended the singlet scalar? We have extended this singlet scalar with some extra additional fermion. Then why we extended this? Because I already told you that present direct detection and Higgs invisible decay width is most of the parameter is ruled out from this experimental constant, direct detection constant, or Higgs invisible decay width. So in the presence of in the addition of this extra fermion, you can have this extra interaction term in this model. So in the presence of this interaction term, you get a large parameter space which can explain relic density. Even you can get relic density from KV to TeV depending on which type of dark matter we are considering. So in this model, actually we have checked that both of weakly interacting massive particle scenario and field interacting massive particle we have checked. Okay, so that I will tell you after some time. Okay, so in this model, let us try to understand what is the model. This is the present interaction term. So this term also helped to get the neutrino mass through radiative seesaw mechanism, and this term actually helped to get the neutrino mass for large region of parameter space through seesaw, through weakly for the weakly interactive massive particle, and for if you consider the feebly interactive massive particle. And in this, and there is a, you can see there is a charge. We have considered these two charges, so that can mix together, and it gives two eigenvalue value U1 and U2 after mixing, and this is the mixing angle. Okay, and in this model, one can see that E1 for the G2 odd scalar fermion, E1 is the light, E1 charge plus charge is the lightest one, and then M kind 10 and then M2. Okay, this is the mass relation. So in this model, that fermion cannot be the dark matter, but one can say again consider that scalar is the dark matter. So now, first, let us consider how one can get a large parameter space in WIMP-like scenario. So let us understand what is the WIMP-like scenario. So WIMP-like scenario is that you consider you consider the dark matter density at early universe is exactly equal to the other particle, and it means when temperatures decreases, it after some time it freezes out and the number of density constant. So this is the main thing of the WIMP mechanism. So in this model, this particular diagram, this diagram basically, let us let us try to forget the fermion. So if there is only singlet scalar, then this diagram actually play the role to calculate the relic density. But one can see that this diagram also affect the from the to the direct detection cross section. That's why it is ruled out. So in the presence of extra fermion, so this basically T and U channel diagram through this extra fermion can help you to get the relic density, and most of the parameter space is not right now is not ruled out. So extra additional effect come from this interaction term, and also you can get extra effect from this co-annihilation term. So that's why you can both this annihilation channel and this co-annihilation channel play a crucial role to give a relic density through freeze out mechanism, and you can get large parameter space for this for this dark matter. Now what we get, so if we only, let us see, this is this parameter space we get for this particular, which consider this mass. Okay, for E1 and E2 mass we have considered. Now you can see that both this blue region, this means if there is only single scalar, you just get only one line, this two line you can get relic density. But in this model, you can get full region, which is every all this region is satisfied by the relic density exactly. You can get up to 10 GB, means you can also calculate the dark matter mass 10 GB, and it is allowed from the Higgs invisible decay width. So in this plot again we have so here in this plot we have varied, actually in this parameter space we have varied kappa versus dark matter mass. Also we have varied this that equa coupling YF. So basically this one, so that we get this parameter. So similarly, this point also plotted in kappa versus Higgs total coupling versus equiplane, and we get this type of structure. So in this white region, outer white region, it is basically it's give the it's not give the exact relic density, it's give less relic density. So that's why we do not take this parameter. And this basically inside white region, this is actually it's ruled out from the larger relic density and from the direct detection experiment. Okay, from the direct detection experiment. Okay, sorry. Okay. So one can see that in this model you can get large region parameter. You can explain large region parameter space, which can explain the relic density. Okay, now this is the parameters of benchmark. A few benchmark point I have shown. So this is what you can get the relic density at the when the dark matter mass is changed through this process, freeze out mechanism. Now can we in this model can we get dark matter through freeze in mechanism? So what let me tell you what is the freeze in mechanism. So in WIMP mechanism we consider that dark matter is in equilibrium at the early universe, means that dark matter density is equal to the other particles. But here in freeze in mechanism we consider the dark matter is not in thermal equilibrium, and the number density of the dark matter at a very early universe is 0, and the dark matter get populated or it produces from the decay of some other particle or annihilation from other particles. So dark matter get produced from some other heavy particle. Okay, so so that is the condition. And how we calculate the thermal equilibrium? That's gamma by H ratio. You have to calculate it. H is the Hubble constant, gamma is the interaction rate, and if the decay it coming from the decay, then gamma you can convert, it is just like a decay. You can calculate it. Okay, and for freeze in mechanism we consider that it is not thermally equivalent, so gamma by H it less than 1. And now one thing that, so it produces from the some heavy mother particle. So in that case, whether the mother particle, if the mother particle are in thermally equilibrium with the other particle, then you do not need to solve, you can solve the only evolution equation for the dark matter. But if the dark matter is not in thermally equilibrium, then in that case, and the mother particle produces from some other heavy particle, in that case you have to solve various coupled differential equation to get the dark matter relic density. Okay, so this you have to consider, means you have to take very carefully whether your mother particle is in thermally equilibrium or not. So that you have to take very carefully. Okay, so now in this model, what in the presence of singlet scalar model, we find that all this heavy mother particle is in thermally equilibrium. So we have only solved the evolution equation for the dark matter. Okay. Then this is the simple formula for means after solving this Boltzmann equation, we get the simple formula in this model, and you can calculate the relic density. Now one thing here, basically I have considered only the decay with formula, or it also have contribution from the annihilation, but we have already checked that if the similar coupling is involved in the decay with and the annihilation, then in that case the decay with always dominate the contribution. So that's why, means we have checked that it is more than 10⁶ times than the annihilation cross section. So that's why in this particular scenario we have neglected, we have considered actually, but you can neglected this from the analytical expression. Okay, and also one thing that in the decay with, if the 2-body 3-body decay with is present, then always you can neglect the 3-body decay because of the extra additional propagator suppression. Okay, so in this model, this basically these two diagram actually involved to give the relic density. So we have calculated it, and we found that dark matter from KV to TeV region, one can calculate the relic density for depending on the this very small equa coupling or
So
this.
Najim,
yes sir,
there is a question. So Abhishek, you can ask the question directly.
Am I audible?
Yes.
Can you go to the slide where you have an additional contribution for singlet scalar annihilation of dark matter? Yeah, the next slide, slide 7.
Okay.
Now my question is that since the additional channels opens up for dark matter annihilation, right, then the Higgs portal coupling of the dark matter can be reduced in this case, right? Can be lowered down.
Yeah.
So it is the model in the case you are which you are talking about here, the stability of Higgs potential cannot be improved. Am I right here?
No. So I mean, previously I have in this paper I have checked the detailed stability channel, so it can improve. Okay, so in this model, it can also improve, or it can also worse kind of thing. Okay, depend because of this fermion. Okay, that you have to check. But in our model, actually, I should tell you, in our model we choose the parameter in such a way that that all the Higgs potential, scalar potential is stable up to the Planck scale. That we have checked. We choose the parameters specific. So that we have taken care.
Is it because of small Yukawa coupling that you are taking into account for the dark matter production?
Small Yukawa coupling is not doesn't matter. Actually, you can take very small coupling that can also affect your stability, because it is coming to means it goes to us directly on RG analysis. Also, it goes to the potential. Okay, so that can affect. So that very small effect, very small contribution can also change huge change in the lifetime of this electric vacuum. Okay, so that small is not matter. We check the all the other pattern. We choose that other parameter is there. Suppose lambda s is there. We choose it's to be something 0.2 or something. So that's why it is already stable. So you don't have to worry about from the stability point of view in this model. So this is not related to the fermion. This is not related to the smallness of it. So you can put large Yukawa also. So that you can consider.
No, not for large Yukawa. I think it will destabilize the Higgs potential, right? Just like top layer
no. Not means not exactly. You have other parameter. Yes, you are true that this phi coupling is there. This basically this yn is there. So that actually directly affect to the Higgs potential.
Yes.
Okay. So like it come like yn to the power 4 minus yn to yn to the that that will affect. Okay, but you have also this lambda s. Okay, that can also affect. You can play basically. Okay, you can play basically these two parameter all and this Yukawa coupling coming indirectly. It can affect, but indirectly means through other coupling, other differential equation. Okay, so you can play with this, and we have choose all the parameters such a way that your Higgs potential is absolutely stable up to the Planck scale. So there's so that is the thing.
Okay.
I have checked means both. Also, one thing that in this model we check that there is actually in normally Higgs normal standard model, what happen, you get two minima at one at electric scale and one at very high scale. But in this model I find that there may be three minima. Okay, there are some parameter space is there, so you can get some three minima: electric, along the Higgs scalar direction 1, along the singlet scalar direction is 1. So we have checked that, and that your electric potential is just goes above. So there's no stability kind of issue. Okay.
Thank you.
Yes. Okay. So okay, so in this so when we consider that FIMP like scenario, we consider that Higgs boson coupling and the Yukawa coupling to be very small. Why? So one thing I just forgot to tell you, that to get the relic density, and why we call it is feeble, to get the relic density is actually you need this decay. It should be around 10 to the minus 17 or 10 to the minus 19 GeV. Okay, so that you need. So that's why the Higgs boson coupling or whatever the decay with that coupling actually is very small. So it's a very, that's why it's called feeble coupling. So that's why it's called feebly interacting massive particle. Okay, that because of this coupling strength. Okay, so that's why the reason. And one thing other, I just want to say that this heavy particle can also decay to the other particle. So that decay, but you do not have to consider all the other decay channel. You have to consider only the partial decay with which actually produces the dark matter. Okay, so that you have to consider in this decay. You do not have to consider all the other decay channel. Okay, so but when the particle means this mother particle is not in thermally equilibrium, then you have to consider that one, but that is tricky. So means you have to solve this all this differential equation, couple differential equation, but you can get it. So different formula will come, but you can get it. So for in this model, so this is the basic just simple formula, you can get the relic density. And in this model we can find that from kV to TeV region for FIMP dark matter, you can get the relic density depending on this parameter space. Okay, so from the both electric take tweak and look both WIMP and FIMP scenario in this model, we can get from again KB to GeV region, KB to TeV region relic density, which can basically satisfy the relic density. And it is also allowed from all the other experimental concepts like stability, like electron flavor violation concept, like muon G1 has to have very small contribution. So that is also allowed in this parameter space, also allowed. Okay. So now can we satisfy the neutrino mass in this model? Yes, yes. This model also give you neutrino mass through radiative seesaw mechanism, and this basically this equocoupling is there, and there's a Higgs portal coupling is there, that basically play a role to give the neutrino mass. Okay, so in this model we find that you can explain all this parameter, and one thing I just want to say that if you have only one doublet or one fermion singlet, then you cannot explain all this neutrino parameter. So you have to add some one other extra doublet which may or may not affect the dark matter density. Then in that case you can also explain the all this neutrino mass and mixing parameter. Okay, so also in this model we search whether this model in future can we search from at the LHC. Yes, we can search, we can get some signature at the LHC of this heavy particle. So basically we choose in this model we choose a particular process like PP going to E plus E minus, and that E plus minus going to decay to one lepton and dark matter. So in the final state basically it has 2 lepton and missing its signature. Okay, so that analysis, that final state channel we have searched, and in this model basically we have dominant contribution from coming from this PP going to W decay to lepton and neutrino, and PP going to ZW, here 1L get misidentified, and PP going to ZZ, Z going to LL, and Z going to neutrino. So that basically gives you dominant contribution to when you search in terms of LHC Atlas detector or CMS detector. Here basically the other background also is there, but that can be reduced by putting some constant in the final state analysis. So I will talk about later. So this PP going to TT bar, TT going to leptonically, so that can also contribute in this channel. Also Drelian process also gives you additional contribution, but using some additional cut, this basically this background can be neglected. Also some other background is there like PPJJ, where JJ misidentifies as lepton when you have to multiply with the fake rate. So then that also contribute, but that background is very small. Okay, so in this model I should tell you before that what kind of software I have used to calculate the relic density of collider analysis. So first I built this model in FANDUL and SARA. We have verified independently on SARA using the SFINA and MATgraph. So we built this FANDUL for the MATgraph FANDUL file for the MATgraph. We have generated UFO file in the MATgraph. Then we use PTR for inbuilt PTR for the hadronization. Then in finally we use the Delphis with the Atlas configuration part for the collider analysis. Okay, so this software also means we have independent, as I said, we have independently checked with SARA, SFINA, and other software also. Okay. So now going to the again analysis. So this is the basically production cross section for the PP going to E plus E minus particle at LHC 14 TeV. Okay, so so and this is the standard model background cross section. PP going to WW and W going to L nu, W going to L nu and Z going to LL. Okay, that cross section is there in femto1. Okay, and this is the cross section for final state of this process for particular this 3 benchmark point. Okay, for 3 benchmark. Why we choose this 3 benchmark point at lower mass, higher mass, and medium mass, so that we can exclude most of the, actually we plotted a contour region, so we can exclude most of the region from this collider study right in the present day. Okay, so but so we choose this and we have plotted this actually in the final state we consider that PTL is greater than 30 GB. Okay, lepton pseudo rapidity is less than 2.5, and we in the final state actually we consider BZ and the light jet is 0. Actually this condition actually reduces the all the other background like PPTT, Drelian process, PPJJ. That process is reduced by this process and this cut. Okay, and in the final state we consider the 2 same sign opposite sign same flavor opposite sign isolated lepton. Okay, so that we have considered. Okay, and this is the distribution, and we have done the cut-based analysis, and we have checked various variable like PT of lepton, PT sum of the PT of all lepton, transverse missing energy, invariant mass, like delta R of LL, delta phi between LL. We have, but out of them we find that only this invariant mass of LL and transverse missing energy give you the almost good significance. So you do not have to consider all these variables. So what we find for this 3000 femto1 inverse luminosity, and we choose basically three benchmark point. We find the 3 signal region for this is the cut, and we find that we find that for different significance for this 3 benchmark point for this 3 signal region. One can see that for this first signal region you can get that benchmark point. For benchmark point 1 you can get large significance, and you can see for signal region 2 you can get just significance for benchmark point 2, and you can get large significance for benchmark 3 for this signal region 3. Okay, so now using this 3 signal region, we calculated more than 1000 benchmark point, different benchmark point, and we calculate all the significance, and we choose basically 3 set of signal region, and we find the 3 set of significance for this all this point. And out of this we choose the point which actually maximum gives the maximum significance, and we plotted this contour plot so that this actually excluded large region. So for this particular, so this is actually 3000 femto1 inverse we consider. So if you consider 3000 femto1 inverse, so you can get that the future LHC experiment can, if there is no signature, then the future experiment can exclude it up to this region at 5 sigma, or if this excluded at 2 sigma, when you consider but the present experimental data, present LHC data with 139 in femto1 inverse, it already excluded at 5 sigma when that ME plus minus something like 550 or 570 GB, or if you consider 2 sigma it may be 750 GB. It is already total. That details means we have done this collider analysis, and you can say now. So this is for when we did that. This we consider that we weakly interacting massive particles. So now if we consider the feebly interacting massive, can we get a signature at the LHC? Because we don't know what is the type of the dark matter. It can be feebly, it can be anything. Okay, so now if it is feebly, if it happen to be feebly, then can we detect the dark matter at the LHC? Yes. So there is a facility at near the CMS. There is a detector called Mathcal detector. It is a proposed detector. Okay, so that basically will build to measure the charge stack for long-lived massive particle. Okay, so in this model there's a very small coupling. As I said, that mother particle decay with around 10 to the minus 17 GB. So that means the decay lifetime is something around 10 to the minus 9 second or something. Okay, so 10 to the minus 9 second or something. So that basically says that it can produce a large track. So this is the track length for this particle in our model. So in our model, and we have to calculate the number of event in the charge detector. So this is the formula. This is the production cross section. This is luminosity, and this is the formula. So this basically you can find in detail in this reference paper. So this LA and NB is the interaction point where it enter and where it out. Okay, that you have to calculate. So, and in this model for this particular 1500 GB region, we find that to get event greater than number 3, one need the large luminosity. So we have to wait further. But again, I just want to say that if this mass is something 700 GB or something, then you can get within 3000 femto1 inverse, you can get a number of event greater than 3. So in future we have to wait whether this can give you signature. We can get any signature at LHC or not. Okay, so in this model, my conclusion is that we have done the detailed analysis of this model so that in future, if we get any signature at LHC or at any other experiment, so we can either rule out this the most of the parameters, or we can say that yeah, this model may be the correct. But we have to wait for the future experiment. So that's why we have done the detailed analysis for this model. Okay. Also, we also try in this model. We also tried to see whether this because it has contribution to the neutrino mass. So we also tried whether it can affect from the neutrino experiment or not. So still we have not done anything on this model, but we have written some code so that it can also get affected from the neutrino experimental result, like Dune or like new experiment, long baseline experiment is there. So it can basically, this model can produce a effective interaction like from the loop box diagram, like LL neutrino, that coupling is there. So that basically is coming like a NSI non, it coming like a non-standard interaction type of term. So that may in future may affect on this from the, it may basically affected from the neutrino experiment, or it may, this parameter actually it may get constant from this neutrino experiment, or it may solve the degeneracy in the other sector of in neutrino mass parameter or not. Now let us go to the other model. So in this Higgs triplet, I will talk about very small thing, okay, because this is a similar kind of model, but one thing is that I just difference is that in the triplet model, extra triplet, this heavy triplet and this heavy charge for charge scalar mass is very small. That's why coinhalation is large. So that's why in this model you can get relic density when the dark matter mass is around 2.3 TeV around. But in the presence of extra fermion, you can, that scenario is completely changed. And in this model we have done only the Feebly dark matter scenario. So in the, if you consider the, here the dark matter is like that NS, or this neutral particle one is the dark matter, okay. And in this model you can get, in the presence of this fermion, you can get Feebly interactive massive particles from KV to TeV region, okay. And also you can explain the neutrino mass in this model too, from the through radiative seesaw mechanism, okay. So this is the mass, this is the Lagrangian of this model in the presence of this extra fermion and extra triplet scalar. And this is the basically mixing angle when the neutrino, all this neutrino, this is the neutral part, basically this neutral part, it has two, we have added 2 doublet and 1 singlet. So this neutral part, actually 3 neutral part is there, so that basically mixes with each other. And we choose the simple one case, so that it if there is, it is not 0, then it is like a PMNS kind of matrix. So you have to add these 3 separate mixing angle. We have done we have also checked that, but let us just choose the simple one first. So it means using this angle, using this mixing matrix, one can get that this chi1 is the lightest one, chi2 is the second lightest, chi3 is the third lightest, and also charge particle also get mixes, and it is there. And in this model, that chi1 can be light, but the previous model we said that dark scalar is the dark matter, but here the fermion candidate is the dark matter. It cannot get fermion dark matter for light fermion, light scalar dark matter, but here you can get light fermion as a dark matter. And so this is the mass expression of this model. I will not talk about, this is the simple mass expression of this model, okay. Let me go to this. So it can, this decay will basically again help to get the relic density. It basically all this mother particle decay to the dark matter particle, and it help to get the relic density. And in this model, basically again you can see that from KV to GV region or TeV region, depending on the parameter space, you can explain the relic density through Feebly interactive massive particle. Also in this model, you can again explain the normal hierarchy, inverted hierarchy, all these parameters. Here I have choose basically 3 benchmark points which exactly explain this normal inverted hierarchy scenario, so that this model can explain this situation, okay. So in this model again, our conclusion is that you can explain KV to TeV dark matter region, means also you can get large region of the parameter space, and neutrino mass also you can explain. And in future it can you can also from the neutrino experiment you can give a stringent mount on this model, but we have not done yet, but our plan is to do, okay. Now I will talk about what recent actually means during in my previously I have not done anything on neutrino basically experiment, okay. So here basically I have learned how to do the neutrino experimental experiment and how to run this code globes or etc. Okay, so previously I have done various model for the stability point of view, like type 1 seesaw, type 2 seesaw, type 3 seesaw model. Also I have done few radiative seesaw model, and how we have calculated the all the detailed parameter space which can give you exactly the relic, exactly the neutrino mass and mixing, and that we have done, okay, for all these various models. And we also from the stability point of view, we have also checked for type 1 and type 3 seesaw, and we also one can say that this model is particular parameters is allowed or not allowed, that we have done. And we have used the the Kasasi-Ibara parameterization such that it can give some good signature from the stability point of view also. So that we have done. But recently I'm learning the globes here basically at IPM Tehran. Okay, so recently I have produced, actually I have generated some plot done by this people, Masood, Payman. So this paper I have reproduced here. So what is the main motivation of this paper? That neutrino parameter, we measure that theta 1,3, theta 2,3, theta 1,2, and also that we measure that M21, M that we have measured, right? So but we don't know what is the exact value of delta, or we don't know normal hierarchy or inverted hierarchy is there, which one is the correct, that we don't know. So in this paper basically they said that that extra, if you have extra additional non-standard interaction in your model, okay, non-interaction term is there, then that oscillation may affected by that oscillation, neutrino oscillation probability get affected by this NSI parameter. So in some point this NSI parameter gives you additional degeneracy, means additional degeneracy on delta or some other parameter too. So they have done that in the presence of, so in this paper they have said that first they have done with the T2, they took the T2K NOVA, this experiment. They said that in the presence of NSI parameter, in the presence of in the presence of NSI parameter, additional degeneracy will come. But if you go to the other experiment like T2K NOVA and the other experiment, so it basically try to reduce the degeneracy. So if you include the experiment, so basically in this actually this plot I have produced here. Okay, so this is basically this plot actually means this type of plot is there in paper. So I have used I have produced this one. So you can see there is a two different theta 2 3 for a single delta CP is there. So there's a degeneracy kind of thing. So if you choose these two experiment is there. So in the presence of epsilon EE parameter, there's a there's a sorry, there is a 3x3 matrix in the NSI parameter. So in the presence of E, if you just forget all these other NSI parameter, so you can see that there's a small, you can see that there's, again, it's almost remain similar. The degeneracy is almost remain similar. Okay, but in the present of moment experiment, this is basically these are actually long baseline experiment. This is actually medium baseline experiment. So in the addition of moment experiment, it is actually proposed experiment from China. So you can see that this degeneracy is almost just reduced at one point. Okay, and I have tried that if we include the Dune experiment also, then it just reduced just 1 point. It just goes to very small. Okay, so this is for the, actually I have produced this plot was there in this paper, so I have produced that one. And so and the second plot actually from the, actually I have tried to produce the Mehdi Masood paper. So he suggests that the Dune experiment also can have some degeneracy in the presence of NSI parameter. So he showed that actually he first he considered that 3.5 years neutrino, 3.5 years anti-neutrino experiment, and from that he get that means some degeneracy is there, but in the presence of other. So basically first they considered the low LE like scenario, low energy neutrino beam. Then also after some he considered the medium energy flux also, and in the presence of both flux they say that this degeneracy can be reduced. That so I have reproduced that one also. Let me go to let me try to understand the Masood paper here. So he said that he calculated the probability for this particular Dune experiment. So this is basically 3.5 years anti-neutrino, 3.5 years neutrino experiment, and he get that that in the presence of this parameter, basically epsilon, this is they consider epsilon e mu. Okay, epsilon e mu is there, so he considered that one here, and he find that there's this change in that phase will change. The probability just get modified modified in the presence of this parameter. Okay, so p mu e probability, the mu to e sector, but p mu is basically disappearance channel. You can say that only this phi e mu and this basically mu tau will affect largely and for this other parameter like e tau will not affect, almost not affect, e almost not affect this probability. Okay, so here also a very small effect is there, that also so that is there. Also he plotted means this kind of degeneracy is there in the presence of epsilon EE. So I also try to produce that one. Yes, so I have not included the other medium energy level. Means I didn't include that one, but you can see that I have actually produced their paper. So it can, again, I get almost similar, not the exactly same, but almost similar plot. Okay, so there's a in the presence of epsilon EE, you can get some degenerate point. It has some additional degeneracy. Okay, so for this suppose epsilon phi e tau epsilon versus phi epsilon tau tau, there's a huge degeneracy is there. So I have produced this plot from the Masood paper. Also, this other for the all the other parameter for 9 parameter I have tried to produce. So it has some degeneracy. Okay, so that I have done means in this time within at Tehran. So that I have done in this globe. So that is the situation. So so these are the publication. Okay, and these are under review. Thank you. Hello.
Thank you, Najim, for your comprehensive talk, and you covered many things, some model and as well as their phenomenology. So now we can ask some questions if you have some question.
Hello.
Yeah.
Yes.
Yeah, in this slide, which is the currently, what have you varied to get this band? I mean, is it delta CP or?
Yeah, delta CP and epsilon E mu varied from -pi to pi. So basically this is along this line delta CP. Okay, and this is basically actually phi E mu is from -pi to pi.
Okay, so you have varied the phase of E mu
phase of and
parameter.
I have considered, so when I varied this phase of E mu, I consider this epsilon E mu as 0.1. Okay, if you take 0 there, so there is no effect. So that's why I have considered as 0.1.
Yeah, that is fine. So we see that this is P. Which channel is it? P mu E or P mu mu?
Yeah, P mu E. Sorry for faint. P mu E. Mu going
so
to.
Are all these plots for P mu E? Or
so this is P mu E. This is P mu mu. Means this is P neutrino, muon neutrino to electron neutrino. This is muon neutrino to muon neutrino. This appearance and this is appearance.
Okay, so we can see E mu and E tau both has a strong effect on mu E channel.
Yes, yes.
And for mu mu channel, this E mu is showing some effect, but I think E tau, the second plot is E tau, right? Second on the bottom row, yeah, this one. This is not showing much effect.
Yeah. Yes, yes. There's no.
Yeah, and what is the third one? It is mu tau.
Mu tau.
Okay, that is also has some
huge effect. Yeah.
Okay, effect of phi mu tau and mu. Okay.
So I have produced all this paper of Masood. I have also some other plot is there, so I have not shown, only the important one I just saw.
Okay. Okay, thanks.
Any other question for Najim? So I don't see any other questions. So let us thank then Najim. Thank you, Najim, for joining us today and giving your seminar. And I wish you good luck. Stay safe there.
Okay, thank you.
And have a nice day.
Thank you.
So please share your slides, and we'll put it on our social media handle so
Okay,
that
okay,
people
okay.
can take a look.
Okay, okay. Thank you. Thank you.
Okay, Najim.
Okay.
Good. Very good.
Thank you. Should I leave or
Yeah.
is there another?
Okay. Okay, Najim.
Okay. Thank you.